Stanford University.
All right, since everything I have here in the way of preliminaries before the real lecture tonight is also in notes that I'm going to have somebody, Kevin or anybody else who wants to put them up. Since I have these here and they're going to be put up, I will start talking about them now, even though maybe not everybody is here. I think it was Byron. Where's Byron? Byron caught an inconsistency in. It's not an inconsistency in my notes. It's an inconsistency between my notes and everybody else's notes. If you stick with a convention and you never change, you'll be okay, and I do. The trouble is, my conventions are at some point are different than everybody else's. This is a common thing for me. It happens to me all the time. And the reason is I can't stand reading other people's equations. For me, it's an easier thing to write a textbook than to read a textbook. It really is. So when I sit down to prepare a course, I do it step by step by step, working out the equations, working out the details. And I tend to work them out in my own notations, which over the years have never necessarily been made consistent with everybody else's. So there's always some point in the class where I have to tell, not always, but sometimes there's a point in the class which I have to tell people, my conventions are different than other people's conventions. Here's the connection. I'll do that now. Apparently, my Maxwell equations are different than Maxwell's equations. A couple of signs, no more than a couple of signs, but those signs actually are just conventions, and I'll tell you precisely how to relate the two sets of conventions. First of all, it has to do with the definition of the electric field. Let me write down first E sub m. M is not an index here. It stands for Max, or Maxwell. Maxwell's definition of the electric field is, in terms of the vector potential in particular, its connection with the vector potential is that it's equal to it's a vector, of course. It's a vector in space, an ordinary spatial vector. And so it is equal to minus the derivative of the same component of the vector potential divided by dt. So there's one term in it which has the time derivative of the vector potential. The vector potential now, I mean the three-component vector potential. If I wanted to stick some indices on here, I would say that this might be the x or y or z component of the electric field being related to the x or y or z component of the time derivative of the vector potential, and then plus the gradient, which is also a vector operation, of the time component of the vector potential. That's Maxwell. Where he got that from, I don't know. My definition that I have been using, this is Max's, this is Len's, is exactly the opposite, plus dA by dt minus gradient of A naught. Just a definition. You can do it any way you want. Just make sure at the end of the day that the things that you're calculating to compare with experiment are being compared in a consistent way. And so, to put it shortly, my definition and Maxwell's definition differ by a minus sign. That's it. Actually, we'll see there's another convention that will also have to change a little bit. But if Maxwell's equations, the equations that Maxwell wrote down, are of the form del cross E, this is Maxwell, is equal to minus dB by dt. Now, incidentally, we all agree on the definition of B, I'll write it down, that B is just equal to the curl of the vector potential. That Maxwell and I agree about. When I say Maxwell and I, he's not around to defend himself. I mean the conventions. The conventions agree, so I don't have to indicate with the magnetic field whose conventions I'm using. They're the same. All right, so if Maxwell has that equation, let's write what Maxwell would write down. He would also write down del dot B equals 0. He would write down del cross B equals dE Maxwell by dt plus J. Now, whose convention is J, positive or negative? The convention about J was established actually not by Maxwell, but by Benjamin Franklin. All right. So with Franklin's definition of J and rho, current and charge density, in which the electron carries a negative charge, we would put here Franklin's definition of J, and we would also write down del dot E, the divergence of the electric field, is the charge density, but with Franklin's notation for charge. All right? Currents through wires being carried by electrons are negative. All right, now, if you make the following changes of convention, you change the sign of the electric field, that changes the relative sign of these two, and it turns it into del cross Leonard's electric field is plus dB by dt. Del dot B equals 0, that doesn't change. Del cross B becomes minus Lenz's notation for the electric field. But since my notation for current is opposite of Franklin's, this becomes minus J Leonard. How about this one here? This one doesn't change because both the sign of the electric field and the sign of the charge density, if I use the L notation, doesn't change. All right, so the main point is here that through partly historical glitches and partly glitches in my own notes, I wound up with a notation for electric field, which was the opposite of the Maxwell, and so we wound up with some minus signs. The importance of it is just to be consistent. To be consistent, carry through consistently, and of course, at the end of the day, if you're looking up or you're trying to compare your theory with an experiment that's published in the Physical Review, and the Physical Review quotes a number for the electric field, you better make sure that your electric field is normalized in the same way, or has the same convention. The number of times in my life I have ever had to actually compare with a number from the Physical Review has been very small. So until Byron's message, I never knew that I had the wrong sign for the electric field. Okay, that's true. Most likely, when I was teaching undergraduates, I probably corrected. This is probably not the first time I've done this. Had this little. All right. Now the next thing I want to preliminary that I want to discuss is the notion of momentum. We have at least 3 concepts of momentum, and at least 2 of them will come up tonight, maybe all 3. So I want to just go over the 3 concepts of momentum, and they're different. They're not the same. They're not 3 concepts or 3 ways of thinking about the same thing. there are three ways of thinking about three different things, things which in general have different values, different numerical values. The first concept of momentum, mechanical momentum, it's usually called mechanical momentum. I'll write it out, mechanical momentum. That's the thing we write when we write mechanical, call it mechanical P. Mechanical P is just equal to mass times velocity. I'll assume we know what mass is, I'll assume we know what velocity is, or in other words, that P sub m, the mth component, x, y, or z, of momentum is the total mass of a system times the time derivative of, in fact, it really is the time derivative of the center of mass position. If it's a single particle, then it's just the position of that particle. If it's a complex system, then it's just the center of mass position. And that's the notion of mechanical momentum. All right? Next, the concept of canonical momentum. This is a more abstract. The canonical momentum. And that comes about when we start thinking about the Lagrangian formulation of mechanics. We have a Lagrangian of some sort. So, all right, let's start over here. We have a Lagrangian. And the Lagrangian L, I'm going to use for the Lagrangian, I'm going to use the square L and not the script L for the moment. It's a function of a set of coordinates called qi and their time derivatives, qi dot. This doesn't mean some particular qi. It means the set of coordinates and the set of time derivatives. And depending on the structure of that Lagrangian, it may begin with q dot 1/2 m q dot squared, or it may start with something else. The Lagrangian may have a more general, more complex form, but the definition of canonical momentum, and now I'll write it as P sub I. The ith canonical momentum is associated with the ith canonical coordinate, and it's just equal to the derivative of the Lagrangian with respect to qi dot. If the Lagrangian, if the coordinates q happen to be called x is q, and if the Lagrangian happens to be L equals 1/2 the mass of a particle, for example, times q dot squared I, or n, or whatever it happens to be, I'll use I in this equation, qi dot squared, plus perhaps some potential energy, or minus some potential energy, v of x, then the derivative of the Lagrangian with respect to the velocity is just the mechanical momentum. Okay? So in that case, for this simple Lagrangian, the canonical momentum and the mechanical momentum are the same. And for a wide class of Lagrangians, in which the kinetic energy is just expressed as the sums of masses times x dot squared. Right. But I'll give you an example where it's not true, where it's not correct, where the two kind of momenta are not the same. If a particle is coupled or is in the presence of a magnetic field, you can either get this from things we did this quarter, or you can go back to the notes on classical mechanics, where we did discuss particles in magnetic fields. Then the additional term representing the particle motion in the magnetic field, I think it's a minus if I remember, but again, I might have this sign wrong here. The electric charge, if you want to keep track of speeds of light, you can put them in the denominator here, but I don't want to do that now, minus the electric charge times the velocity dotted into the vector potential, or just a xi dot ai. That's the vector potential. From this we can derive the Lorentz force law by working out the Lagrangian equations of motion, but the only thing I'm emphasizing now is that the canonical momentum conjugate to xi now, P sub I, is not just mxi dot, but it also has a term from here, minus E a sub I. This is the canonical momentum, right? The canonical moment, the right words to say is that the canonical momentum is the mechanical momentum plus a piece coming from the vector potential. When we, yeah, okay, so that's, when we write Hamilton's equations, for example, when we do the canonical thing, when we do the mathematics of classical mechanics in Hamiltonian form, for example, the momentum always means the canonical momentum. That doesn't mean we don't want to sometimes shift everything into an equation so that on the left-hand side you have m, let's say x double dot, acceleration. You might want to write equations so that this thing appears on the left-hand side of the equation, but still, the canonical momentum is this object over here. The last notion of momentum, which also in many cases, in some cases, agrees with the mechanical momentum or the canonical momentum, sometimes does, sometimes it doesn't, is the quantity which is conserved by virtue of Noether's theorem if the physical setup is translation invariant with respect to translations of space. In other words, if nothing changes, if the Lagrangian doesn't change, when you shift coordinates, x goes to x plus a constant, then there is a conserved quantity, and that quantity is called also momentum. So it's yet another thing. It may or may not be equal to this. It may or may not be equal to this. It's the quantity conserved by virtue of translation invariance. It is also unfortunately called P sub m, either sub m or super m, depending on whether you're using relativistic notation or not. But we're going to need that quantity. So let's remind ourselves what it is. I'm just going to call it Q for quantity, okay? Well, I won't call it P for the moment. If you have a symmetry so that when the symmetry operation is performed, the Q's transform. Let's suppose each Q goes, when you do the transformation operation, let's say Q sub I prime, the transformed Q sub I, is equal to Q sub I plus, let's say, a small infinitesimal correction, which we can call delta sub I, delta of Q sub I, if we have a symmetry, which means a transformation of this type under which the Lagrangian doesn't change. If the Lagrangian, the magnitude, the value of the Lagrangian doesn't change, then there's a conserved quantity, capital Q, which is equal to the sum over all the coordinates, there's a contribution from each coordinate, of P sub I, the canonical momentum, not the mechanical momentum, but the canonical momentum, times delta Q sub I. So for example, if Q happens to be x, the x position of a particle, if Q happens to be the x position of a particle, then when you translate x, when you translate the coordinates, all that happens to x is it shifts by a little amount. And the amount that it shifts by is independent of x. So you can say in that case that the delta Q sub I, or the delta x, is just a constant, just a number, the amount that you shift by. In that case, this delta Q sub I is just a number, and we find a quantity which is just proportional to the total momentum of the system, the total, in fact, typically the total mechanical momentum of the system, if mechanical and canonical momentum are the same. So one last concept of momentum is as a conserved quantity where you construct it by figuring out how all the coordinates in the system, all the canonical coordinates in the system change when you do the operation, and then multiplying those small changes by their conjugate momentum and adding them all up. And that gives you the conserved quantity, which is also called momentum. I just called it Q here for quantity, but it's conserved if the world is translationally invariant. All right, those are the three concepts of momentum. And as I said, they're not necessarily the same as each other. When the Lagrangian has the usual simple form of a sum of kinetic energies plus potential energies, ordinary potential energies, not this kind of thing, if they're just a sum of the usual kinds of kinetic energies and a potential energy, then they all tend to be the same thing, the various definitions. But more generally, they're not. Okay. Now I want to move on to the relationship between mechanics and field theory. We've used it. We've used the Lagrangian form for field theory, but I want to spell it out in some detail now. Where's my eraser? Ah, okay. All right, we don't need this now. I want to spell out in detail in what sense field theory is just a version of classical mechanics. But the reason I'm going there is because I want to get to these questions of conserved quantities, conserved momenta, and also the conserved energy. Before doing that, let me put over here, right in the corner over here, the concept of energy in classical mechanics. The concept of energy becomes important when the Lagrangian is invariant under time translations. T goes to T plus a constant. In other words, when the answer to a question doesn't depend on the time that you start the experiment. I'll just write down the formulas, not derive them. Given a Lagrangian, which is a function of Q's and Q dots, there's another quantity called, sorry, no good, L, square L. There's another quantity called the Hamiltonian. The Hamiltonian is conserved, and it is the energy. Just to remind you, it's given by the sum over all the coordinates, whatever coordinates describe the system, of the canonical momentum conjugate to the ith coordinate times the time derivative of the ith coordinate minus the Lagrangian. While we're at it, why don't we work this out for the simple case, just to remind you. If the Q happens to be x, if it happens to just be a coordinate, and the Lagrangian is 1/2 m x dot squared minus v of x, a potential energy, a function of x, let's just work out what the Hamiltonian is. All right. First of all, there's the canonical momentum. The canonical momentum is the derivative of the Lagrangian with respect to the velocity. So P, in this case, is just equal to mx dot, just exactly what you'd expect. If we multiply that by Q dot, in this case, there's only one coordinate in the problem, just x. Then we would get Px dot, which would just be mx dot squared. One x dot comes from the Q dot, the other one comes from the P. So it's mx dot squared, and then minus the Lagrangian. So minus this term, minus 1/2 mx dot squared, this one, and then minus v, or plus v. Two minus signs giving you a plus sign. Okay, the mx dot squared and the minus 1/2 mx dot squared just give you plus half mx dot squared. So what do you get? You get the sum of kinetic energy plus potential energy. Just the definition. The definition of potential energy and kinetic energy in the case where they apply, where you can separate the Lagrangian nicely into quadratic things in coordinate and time derivatives and other pieces which don't depend on time derivatives. It's in that case where there's things which are quadratic in time derivatives and other things which don't contain time derivatives, that there's a well-defined separation into kinetic energy and potential energy. The kinetic energy is just the quadratic expression in terms of velocities. The potential energy is the piece in the Lagrangian which doesn't depend on time derivatives. That's it. Notice that in the Hamiltonian, the energy, it's T, or kinetic energy, plus potential energy. In the Lagrangian, it's kinetic energy minus potential energy. So in any case, if the Lagrangian is of the simple form of squares of velocities plus things which don't, or minus things which don't depend on velocities, you can usually read off very quickly, without doing any work, what the Hamiltonian is from the Lagrangian. You just change the sign of the term which doesn't contain velocities. Okay, that's it. That's the whole prescription. And we can use that, but we should remember that it really comes from... What was the point of this Hamiltonian? The point of this Hamiltonian is it's very easy, go back to your classical mechanics notes, using Lagrange's equations to prove that this is conserved, that it doesn't change with time, that the equations of motion, Lagrangian equations of motion applied to everything on this side here, will tell you that the Hamiltonian is conserved, and it is, of course, the energy. It is, of course, the energy expressed in a somewhat unfamiliar form, total energy. Okay, now let's come to field theory. Field theory is a special case of ordinary classical mechanics, slightly obscured when we try to write it in relativistic fashion. If we want to see the close connection between field theory and classical mechanics, it is best to give up this whole enterprise of trying to keep all equations explicitly invariant under Lorentz transformation, and to just say, let's pick somebody's time, your time or my time, but pick a time variable. In other words, pick a frame of reference and stick with that frame of reference, and don't for the moment worry about going back and forth between different frames of reference. We'll do that later. Pick a frame of reference, pick a time. Don't try to keep the equations invariant under Lorentz transformation. And it is easier in that form to see the connection with classical mechanics. Okay, so I'll leave this up here, but let's come over to here. All right, classical mechanics, you have a time axis, and you have a collection of things, Q sub I of t, and you have an action principle. The action principle is Lagrangian as a function of q and q dot, or all the q's and q dots, dt. That's the action. And the action principle is the principle of least action. That's it. A time axis, a set of coordinates which depend on the time axis, an expression for the action which is an integral over time, and a principal variation of the action, or the action is a stationary point. All right, so now to go from here to field theory, again, we have a time axis, and the coordinates of the system are functions of time. But what are the coordinates of the system? The coordinates of the system are not labeled by an index, a discrete index I. The coordinates of the system are labeled by position. They are the values of the fields at each position in space. If we wanted to, we could imagine that space was discrete, and have x go horizontally, but the only relevant points would be some discrete collection of points, and then say the values of the fields at each position would define a coordinate. The field over here, the field over here, the field over here, the field over here, and so forth. This might be called phi 0, this might be called phi 1, this might be called phi 2, and so forth. And the q's, the canonical coordinates, would be the phi's. And instead of writing phi I to indicate which green line the phi is on, I'll just accept the fact that there's an x-axis and write phi of x. So at each point x, there's a separate and independent field, or a separate and independent coordinate. Now, I don't use coordinate to mean x. I mean to use coordinate in the same sense that we use q. Degree of freedom. Perhaps degree of freedom is a better word. Yeah, let's call it degree of freedom. Phi of x is a degree of freedom, and x is simply a label in the same sense that I is a label. Okay, so we shouldn't get confused between coordinates and labels. Right. There's also, of course, time derivatives. Those are like the q dots. Now, Lagrangians also depend not only on phi at each point, but they also depend on derivatives with respect to space. Let's think about that for a moment. In other words, they depend on things like d phi by dx, not d phi by dt, but d phi by dx. Typical Lagrangian density, typical Lagrangian for a field theory. But what is phi, derivative of phi with respect to x? Okay. What is it? It's really another way of writing. Let's say the distance between these points is called epsilon, where epsilon is small. It's really a way of writing phi at a point x plus epsilon minus phi at a point x divided by epsilon. And so the derivative is really just a function of the phi's. It doesn't, the most important thing is it doesn't involve phi dot. So in places where the Lagrangian might depend on spatial derivatives, that's really part of its dependence on the phi's. In this case, it might depend on two phi's at the same time, but there's nothing to say that a Lagrangian can't depend on two q's at the same time. It could depend on q1 minus q2 or something like that. Here it's depending on phi at one point minus phi at the other point. So, yeah.
So you've got phi dot of x.
Yeah.
And so phi is not explicitly a function of time.
No, it's not explicitly. No, it is. Whoa, be careful. It's not depending on time because x depends on time. X is just a label. X is just a label. We could, instead of calling this the x-axis, we could call it the numerical axis I. And this would be phi of phi I.
So why don't you write phi of x and t?
Yeah, that's right. Phi is in general a function of x and t. In the same sense that q depends on I and t. It depends on I just because it depends on which one you're talking about. You're talking about q1 or you're talking about q2. Here, are you talking about phi at one point or are you talking about phi at another point?
So just one more follow-up. So you treat each one of those phi's as an independent variable?
You treat each one of them as an independent canonical degree of freedom.
What about the sort of continuity constraints of space?
All right, that's a very good question. That's a very good question. And the answer is if you write the right kind of Lagrangian or the right kind of Hamiltonian, then sudden abrupt changes in phi from one point to another will be very costly in energy. So the dynamics is what right. That we'll come to that. That's a very, very good point. What is it that requires the phi to vary smoothly between 2 points? Yeah. And the answer is energy. But we'll see. Well, I'll show you how that works. Okay, so now let's think about what we would mean by a Lagrangian, or better yet, an action. An action in classical mechanics is always an integral over time. So it's an integral dt of a Lagrangian, L. But now, the Lagrangian itself is going to be a sum over space, or an integral over space. We've already done this kind of thing. We've done this kind of thing. I'm simply repeating what we did earlier, that the Lagrangian, or the action itself, is an integral over space and time. But if we separate off the time integral and write it as an integral dt of square L, then write this as integral dt times the integral dx. And what does dx mean? It can mean one, incidentally, I did not mean to imply that space is one-dimensional. We might have several dimensions of space, but you get the idea. This could be d3x, dx, dy, dz, of a Lagrange density. The script L, the thing that we've called script L in field theory, which depends, what does it depend on? It depends on the field at point x, it depends on the time derivative, and it may also, and generally does, depend on d phi by dx. I'm going back to earlier notations where we wrote the Lagrangian density here in terms of phi and derivatives of phi, but now I'm keeping separate the idea of time derivatives and space derivatives. I don't want to mix them up into a single common notation now. Time derivatives and space derivatives. And the space derivatives here, they are just differences of phi. So really I could just think of this as a function of all of the phis and the phi dots. Because this is really just, if you know all the phis, you also know the differences. But I'll keep it in this form, separate off in this form. And the square Lagrangian, in other words, this Lagrangian here, which gets integrated over t, this is it. The Lagrangian itself is an integral of a Lagrange density. There's a notion of a density of Lagrangian. That meaning to say, you integrate it over space to find out what the full Lagrangian is. You can think of it as a sum of terms, each term involving the field, the time derivative of the field, and perhaps neighboring values of the field. Okay. I think that's reasonably clear. Now, let's now think about what's up here. Let's go for the Hamiltonian. After all, this is a special case of mechanics. Yeah. And that may, I think that's right. That is right. All right. Now, field theories, like Maxwell's theory, other field theories, certainly have a notion of energy associated with them. Light waves have a notion of energy associated with them. Light wave shines on a bucket of water and it heats it up. It heats it up because it transfers energy to the molecules. It turns into thermal energy. So fields have energy. They're not, in that sense, they're not something entirely new, and that energy is part of the universal conserved energy that is associated with time translation. We should be able to use the formulas that we have there if we apply them correctly to this kind of special case. So I want to go through that with you. First thing, how do you construct the energy? So we want the Hamiltonian. The first thing we need the P's and the Q's. The P's, the Q dots, and we need the Lagrangian. Okay, so what are the P's? The P's now do not mean momentum in the sense of mv. They have nothing whatever to do with that. They are the derivatives of the Lagrangian, with respect to the velocities. And what does velocity mean here? It means a phi dot. It doesn't mean velocity in space. It means velocity in field space. How fast the field is changing at a particular point. Not changing because you're going from point to point, but changing because the field at any given point changes. All right, so the notion of a P conjugate to a particular phi, we need a notation for it. And the reason we need a notation for it is because we've already called too many things P. All right? We've called too many things P, and there is a standard notation. What are we talking about? We're talking about the derivative of the Lagrangian with respect to phi dot. We look for the phi dot. It actually doesn't matter if the Lagrangian, and we'll assume this, we'll assume that the Lagrangian, at each term in the Lagrangian, at any given point x, only involves the phi dot at that point of x. So therefore, when you differentiate the total Lagrangian, it only picks the particular point. Yeah. All right, so we're interested in derivative of Lagrangian with respect to phi dot, and that is the canonical momentum conjugate to phi. I don't want to call it p because we're going to save p for something else, so the standard notation for it is pi. Sometimes pi sub phi. In other words, the canonical momentum conjugate to the coordinate phi, and both sides are functions of position. This is a function of position, and this canonical momentum is also a function of position. Now, if there are many fields in a problem, there may be many fields in a problem, not just phi, but phi 1, phi 2, phi 3, and maybe a few A's and maybe a few other kinds of fields. Then there will be one of these for each kind of field, right? And this will be there. So that's pi. It's associated with the field at a point x, and it's replacing the p over here. Okay, so now we're in a position to compute the Lagrangian, the Hamiltonian. Let's compute the Hamiltonian over here. H. Now, first of all, it's a sum over all I. What does I stand for in this problem? I stands for x. I and x are the same thing. They're the labels that label the degrees of freedom. Right? So, the sum over I is really going to be an integral over x, integral dx. Sum over all positions. That's it. Now, what's it going to have in it? It's going to have p sub I, that's pi sub I, of x, times phi dot of x. This is an integral over x, and it has pi, the subject over here, whatever it is. We're going to do an example, so we'll see how this works soon enough. Then minus the total Lagrangian. But the Lagrangian is also, sorry, this is correct. This is correct, but let me,
Yeah, what's the I?
Which I? No I. Right, that's redundant. That's redundant, good. No I. Right. Now we have to subtract off the total Lagrangian. But the total Lagrangian is just this thing here, which is also an integral. So under the integral sign, under the integral d cubed x, this is d cubed x, we have to subtract off minus the Lagrangian density. As I said, we'll work out an example soon enough. But let's look at what we have. We have an energy which is expressed as an integral over space. What would you call this thing in the bracket? Called the energy density. The energy density, and that's exactly what it is. This object is the energy density. The thing inside the square bracket over here. Okay, so now we're cooking. I think we don't need this picture. Let's put this picture up here. X, phi of x, p. Okay. Get rid of the picture. And let's do an example to see how this works. The example that we've used over and over, let's just take one dimension of space. Do as many dimensions as you like, but let's just do it with one dimension. All right, Lagrangian density. It has a kinetic energy term, 1/2 phi dot squared. Remember, the Lagrangian contains phi and phi dot. Right. Let's put in minus 1/2 partial of phi with respect to x squared. And finally, let's add in, just for generality, some sort of v of phi. In other words, we'll call, let's just call it v of phi. Let's call it v of phi. It has phi dot squared, it has gradient of phi squared, and it has v of phi. If we went back to thinking about relativity, we would recognize this quantity here as a scalar and this quantity here as a scalar, and we would be doing the same kind of constructions we did when we thought about relativity, and we would sort of combine these two things and call them something like 1/2 d mu phi d mu phi. And that's a nice, beautiful relativistic way to write it, but we don't want to mix them up in that form now. We want to keep separate time derivatives and space derivatives. Okay, let's now ask, what is pi sub phi? Pi sub phi is the derivative of the Lagrangian with respect to phi dot. And that's just phi dot. It's pretty easy. Did I write it here? Yeah, pi sub pi, or just pi, is just plain phi dot. It's easy. Now let's work out the Hamiltonian, or the energy. The energy is integral dx of pi sub phi times phi dot. Pi sub phi is phi dot, so there's phi dot squared. Then there's minus, that's this whole thing here. And then there's minus the Lagrangian. So minus, here's the Lagrange density here. So that we can just read it off. Phi dot squared minus 1/2 phi dot squared. That's going to give me just 1/2 phi dot squared, right? Phi dot squared minus 1/2 phi dot squared. Now we're also going to subtract off this thing. Oh, this is wrong. Let's get this right. We're going to subtract off this thing, which already has a minus sign. Two minus signs make a plus sign. So this becomes plus derivative of phi with respect to x squared plus v of x. Whoops. I know. Okay, let's see what we have. In the Lagrangian, we have a kinetic energy related to time derivatives, and we have another term which doesn't have time derivatives in it. Obviously, this whole thing is playing the role of potential energy, a piece of the energy which doesn't have time derivatives. Sometimes people call this the field potential energy, but it's really this whole combination, everything which doesn't contain any time derivatives, which is a kind of potential energy. All that's happening is, again, we have kinetic energy, and then instead of minus potential energy, we have plus potential energy in the Hamiltonian. This is the energy of a field. The time derivatives are positive. The space derivatives are positive. Okay. The space derivatives are positive. And if v is a positive function, this would also be positive. What's that? V of phi, sorry, V of phi, very good. V of phi. It's also a function of x, but V of phi. All right, depending on V of phi, I want to concentrate mostly on these terms. They're both positive. The Lagrangian has positive and negative terms. It's not, in general, positive. Right? The energy only has positive terms. Of course, it can be zero. But what's the only way that this thing can be zero here? The only way it can be zero is if phi is constant, so that its derivatives are all zero. One example being phi is equal to 0. If phi is equal to 0, this and this are just 0, but it can't be negative. So energy is typically something which doesn't go negative, yeah.
So in normal mechanics, potential V is arbitrary, so it can't be negative.
It can be negative here too, but you can get into trouble if it's unbounded from below. If it's bounded from below, then you can just add a constant to it and make it positive, and it doesn't change anything. So you can arbitrarily assume that this is positive. If it's not bounded from below, the theory is not stable and it just goes to hell in a handwagon. You don't want any part of such a theory. So you can assume that this is positive also. And then the energy is above 0. The only configurations in which it's equal to 0 is when phi is constant. and probably also at the minimum of this potential here. That's just what substitutes for empty space. Yes, sir, Kevin.
Could you repeat when you got the Lagrange density? Was that just a past?
Well, yeah, that's just a past. Yes, this when we study the field, a scalar field in relativity theory, we used a couple of principles. The first being locality. All right, locality means it depends on the field and its derivatives. We used the principle that it should be Lorentz invariant. Lorentz invariant means it should be made of scalars. And this is just the scalar obtained from d mu phi. That's what this is, phi dot squared minus spatial gradient of phi squared. The minus sign is that funny minus sign which comes into relativity all the time. Okay, so not first thing we found tonight, but an important thing we find tonight is the notion of field energy, and especially field energy density. The energy is an integral over space of a field energy density. I'm going to give that the energy density a new name. Let's take away the integral. We're going to call this the field energy density, and we're going to give it a funny name. We're going to call it T naught naught. The T, I have no idea where that comes from, but I will tell you where the noughts and noughts comes from. I guess I can erase this for the time being, yeah.
So, as you're erasing that, could you say more about the assumption why it's okay to use Cisco instead of Waco?
Yeah, yes. As long as the Lagrangian is an integral over space where at each point, it's an integral over space, so it's an integral of this form, and at each point of space, it involves phi and phi dot at that point, the time derivative of phi at that point. Then when you go to differentiate the total Lagrangian, let's get rid of this integral over t here. Actually, just get rid of this, just Lagrangian is equal to this. When you go to differentiate the Lagrangian with respect to phi dot, let's say phi dot at some specific point. Let's go to some specific point right over here. We're going to differentiate the Lagrangian with respect to the phi dot over here. Well, where does that phi dot occur? It only occurs in one, think of this as a sum. Think of this as a sum over I of Lagrangian of phi and phi dot. Think of it as a sum. Only one term in the sum contains that particular phi dot. The phi dot associated with this particular point only occurs in one term, namely the term associated with that point. If that's the case, if the Lagrangian is built that way, and they usually are, then differentiating with respect to a specific phi dot at a specific point throws away all these terms except one, and that's the point, right. So, yeah. I can't think of any, actually, that's not like that. Yeah, I think they're pathological, at least, yeah, not Lorentz invariant. Offhand, I don't think of it. Okay, but now we're also in a position to answer another question that was asked earlier. Let's suppose that phi jumps. Now, I was asked, what is it that's requiring phi to vary smoothly as the separation between these points? Why can't it be wildly jagged, for example, if they're really independent degrees of freedom? Well, wildly jagged, as you let these distances go to zero, means bigger and bigger derivatives. Remember what the derivative is. It's the difference between phi divided by the small separation. As that small separation gets smaller and smaller, for a given distance, a given difference, the gradient or the derivative gets bigger and bigger, and that would mean that the energy density in here is getting bigger and bigger. So, if you say, I'm interested in finite energies, I'm interested in configurations where the energy is not going off to be something huge, it requires these derivatives to be finite, that the derivatives are finite, that's what controls phi and tells it to be smooth. Okay, is that clear? Yeah, so it's energy that is doing that. All right, what is the T naught naught? I'll tell you where T naught naught comes from. There are two naughts there. T, I don't know where it came from. Stands for something historical. Tension. It does have to do with, yeah, I'm not sure what it has to do with, but the naught naught, that I will explain to you. First of all, in relativity, and this could be, we're interested really in relativistic theories. We're interested in relativistic theories. In relativistic theories, the energy is the time component of a 4-vector. In fact, we usually call that 4-vector P. Too many things are being called P, but we usually call it P, and it's the time component. The energy is the time component of the 4-vector of energy and momentum. Okay? That's one fact I want you to remember, that the energy is in some sense associated with a time component of a 4-vector. And then there's another interesting fact. Whenever you have a conserved quantity in a relativistic theory and a sensible theory, the conservation is local. That means that the quantity just doesn't disappear over here and reappear someplace far away. If there was no locality to the conservation law, then energy or charge or whatever it is could disappear over here and reappear at Alpha Centauri, and an experiment taking place in this laboratory here, for all practical purposes, there would be no energy conservation. That's not the way things work. The way things work, as I explained, is that when you have conserved quantities, they only change if you can detect a flux of them or a current of them passing through the walls of your laboratory. That gave rise to the concept of a density and a current. And the density and the current combined together to form another 4-vector, J mu. The time component of J mu is the density, and the space component of J is the flux or the flow of the current. But in particular, the density, I'm using the language of charge density here now, but think more generally. The density is like the time component of a 4-vector. Well, now we have the density of energy. Energy itself is the 4th component of something, the time component. And density is the 4th component of something, namely a current, a 4-dimensional current. So the density of energy is the density of the time component of a 4-vector. That's why there are 2 zeros up here. One of them stands for the fact that we're talking about energy, and the other one has to do with the fact that we're talking about a density. I think I'll take the second one here to have to do with the energy, and the first one having to do with the fact that it's a density. We can come back later to the continuity equation, which is important, and there is a continuity equation for energy. The continuity equation for energy says that if you see the energy changing someplace, the energy density changing someplace, it's because there's a flow of energy through the system. Okay, so this is T naught naught, and it's the energy density.
Excuse me.
Yeah.
When I hear the word density, I think whatever it's the density of,
Yes.
that thing that's a density of is obtained by doing an integral of the density.
Yes.
Okay, so in the case of the energy there being the first component of that 4-vector, and that it's a density.
Remember that it is equal to the integral of pi phi dot minus L. So this is the thing. The thing in the bracket here is the density.
That's the energy.
That's the energy density. That's the energy density. Right. Very good. It's interesting to ask, all right, if that's the energy density, what is the flow of energy? All right, if we have time, we'll discuss it a bit. Okay. Next, what about the momentum density? Now, by momentum, I don't mean canonical momentum. I mean the momentum which is conserved because of translation invariance. That general concept due to Emmy Noether, that every time there's a symmetry in the world, there's a conserved quantity that goes with it. I am going to call that quantity P. I apologize, there's just too many things called P. Historically, they were related to each other. But now we're talking about momentum in the sense of Noether, having to do with translation invariance. All right, now that quantity, which is a special case of the thing that we call Q, what you have to do to compute it is you sum over all the coordinates of the canonical momentum which now is just pi, the canonical momentum, times, well, let's write it first more generally, P sub Q delta Q. Remember Noether's theorem. We figure out what delta Q is by figuring out how the symmetry operation affects the coordinates, P sub I delta Q sub I. All right, so now we can guess what the form of the answer is going to be. It's going to be sum is going to be replaced by integral. I is replaced by x. So this is going to be an integral over x. P, well, that's just pi. Pi of x, the canonical momentum conjugate to phi. And then we have to figure out what delta phi is. What is delta phi when you make a shift of coordinates? What we're talking about now is a translation of coordinates where the origin of coordinates is displaced from one point to a neighboring point. What happens to phi? Well, what was originally called phi of x now becomes phi. Let's say we shift by amount delta. Let's say we shift by a numerical amount delta, where delta is small. What happens to phi of x? Phi of x becomes phi of x, I guess, minus delta. The point which was originally called x, after the shift of coordinates, becomes called the point x minus delta. Is that clear? The point that was called x, here it was, after we shift the origin, becomes either x minus delta. It doesn't matter whether it's x minus delta or x plus delta. Let's just call it x minus delta. Okay, so what is the change in phi? The change in phi is phi of x minus phi of x minus delta. That's the change in phi when you shift coordinates. Really all it is if I have some field and I move a little bit, how much does the field change? It changes by something proportional to the derivative. Right? So the change in that's how much it changes, and that's of course just proportional to the derivative of phi with respect to x. In other words, the change in the field, when I move my head a little bit to correspond to, when I take all of my coordinate rulers and move them a little bit, the change in phi that I see at a particular point along my rulers is proportional to the derivative of phi with respect to x. So this delta phi just becomes derivative of phi with respect to x. Nice simple formula. Yeah, good. That's right. Why aren't I dividing by delta? Both here, yeah. The answer is, If a thing is conserved, it's conserved after you multiply it by delta. It doesn't matter. Yeah, it's a good question, but the answer is we're just trying to find conserved quantities, and the official definition of the momentum is defined in such a way that that delta is divided out.
I mean, could you think of it as becoming dx in the energy, essentially?
Well,
The delta sort of becomes the infinitesimal dx when you go to the,
yeah.
from the sum to the integral.
Yeah. Right. I think it's defined in a way here which is consistent with previous definitions of the Noether theorem. In any case, this quantity is conserved. It's called P, but it's the space component of a 4-vector. For example, if this is the space component M of the 4-vector, then this would be d phi by dxm, incidentally. We're shifting along the m axis. Each component of the momentum, 1, 2, and 3, each can be represented as the integral of a density. So it's pretty clear that this is the momentum density. This is the momentum density. What sort of notation should we use for it? Well, the first, let's see, I think the second index, all right. It's the momentum density, so we'll call it T. M for the fact that it's the mth component of the momentum that we're talking about, but 0 from the fact that we're talking about a density. We're talking about a density as a density. A density, where did I write it? J mu equals rho and J. So we're talking about somebody's density. That makes this a time component. Whose density? The density of the mth component of momentum. And that's called T0m. T00, that's the density of energy, density of time component. T0m, that's the density of space component of momentum. And we can write it down now. It's equal to pi sub phi, pi, times the derivative of phi with respect to x. I'm sorry I erased it before I rewrote it, but that's what it was. Pi d phi by d phi by dx. Which x? Xm. If we're talking about the x component, then this is x. If we're talking about the y component, it's y, and so forth. Let's work it out now for our simple field theory. Here's our simple field theory. Pi sub phi is phi dot. For this very simple field theory, this is just equal. Pi is phi dot. It's derivative of phi with respect to time. D phi with respect to t. Times d phi with respect to xm. That's the momentum density. A very simple expression. What is this momentum density? I mean, but physically, what is it? For example, for an electromagnetic wave or a wave of phi, well, it literally is the momentum carried by that wave. It's combined together with the momentum carried by all the particles in the system. Incidentally, if you think about translation invariance, the system is only translation invariant if when you translate all the fields, you also translate all the particles. If there are particles, charged particles, and so forth, it's not okay to just translate the electromagnetic waves and not translate the particles. Invariance means you translate everything. So if we were to keep track of not only the field, but all the particles that it might interact with, there would be contributions to the momentum coming from those particles. And we would literally be talking about the conservation of momentum of particles and fields. Well, this blackboard or this whiteboard here is made up out of particles. We can shine light on it. And when we shine light on it, let's say we shine a pulse of light on it. Let's suppose this blackboard were freely hanging freely in space. And we shine a good pulse of light on it. The light reflects off it. The momentum of the light is transferred, or maybe the light might be absorbed. If the light is absorbed, the momentum of the light is absorbed by the system here, and what happens is it recoils. Now, for ordinary light, for an ordinary pulse of light, the momentum is so feeble that it's pretty darn hard to measure the recoil of anything but maybe the lightest filament of some sort, lightest membrane due to light. The ordinary light that you see coming out of a light bulb is extremely feeble in this sense. But, a really powerful laser beam, well, okay, the kind of laser beams that they use across the bay in Livermore have so much momentum that when that momentum is absorbed, the tiny bit of material, the pellet in there, just gets boom, squashed. So yes, light has momentum. Light has energy. Here we've just done it for simple waves. I'm not going to write down, well, let's see. I'm not sure. I want to do this for the electromagnetic field. There's another question that we haven't addressed yet, and I may not address it until next quarter. But the other question is, what is the flow? These are the densities of these quantities. What about the flow or the flux of energy and momentum, the way energy and momentum move? Yeah.
So one question, when we were doing particles, say the Lorentz force case,
Yeah.
you picked a Lagrangian and you said that, the way to prove that you had chosen the right one is that when you do the Euler-Lagrange equations, Newton's laws basically should drop out. So what corresponds to Newton's laws, say in this case where you're doing a field?
And for the simple field here, the equations of motion. Sometimes, especially in modern physics, you don't start with the equations of motion, which you've known for years and years by measurement. You start with a few symmetry principles and some guesses about what the fields are and the Lagrangian. Right, so here we're starting with Lagrangian, but the analog of Newton's laws would be the field equations. d second phi by dt squared minus d second phi by dx squared is equal to minus dv by d phi. Some wave equation.
So, right. I mean, is there another way to prove that your choice of Lagrangian is correct other than showing that this comes out to?
Well, no. You have two ways to start. You can start with a guess about what a Lagrangian is and derive the field equations, or you can start with some experiments and take those experiments and from those experiments derive field equations and then derive an action. So which field is this? The Higgs field? The Higgs field has never really been measured. And this could be, you know what this field could stand for? This field phi could stand for the position of a rope that's stretched between 2 points. Then you could derive it from the fact that the rope is made up out of a bunch of particles. It would just be the kinetic and potential energies of the particles that make up the rope. But more and more, I mean, I think modern physics revolves around trying to guess either from symmetry principles or some basic underlying principles of physics, trying to guess the Lagrangian, and then deriving and often you don't know what the field equations are until you derive them. And then attempt to compare them with experiment. Right, so it's a historical fact. Newton's equations were known before Lagrange's equations. Right. And Maxwell's equations were known before the action formulation of, right. But this gets to be less and less so with time. All right, let's talk about Well, we can go two directions now. We can talk about the flux of momentum and the flux of energy, which I did not want to do right now. Or we can talk about the notion of energy and momentum in electrodynamics, the energy density and momentum density in electrodynamics, in particular for electromagnetic waves. And I think that's probably a more important thing to do right now. The energy momentum, these quantities, T naught M and T naught naught, are some components of a thing called the energy momentum tensor. Energy momentum tensor. The other components of it are associated with the flow of energy and momentum. Maybe we'll get a chance to talk about it yet tonight, I'm not sure. But these objects here are the fluxes and densities of energy momentum, and they play a huge role in general relativity. In general relativity, they play the huge role of being the sources of the gravitational field. So we have to come back to them, but I don't think we have to do that tonight, not necessarily. Let's talk about applying this to the electromagnetic field. Now, we want to apply some of these ideas, particularly the idea of energy momentum in the field momentum. We want to apply those ideas to the electromagnetic field. In fact, we want to apply the whole set of ideas to the electromagnetic field. We could do it using the Lagrangian and the formulation that I gave you earlier in past lectures. The fields, what are the fields? The fields are the components of the vector potential, A mu. There are four components to the vector potential, the time component and the three space components. And the Lagrangian is written in terms of them. The electromagnetic field tensor is written in terms of them, in terms of their derivatives, space derivatives and time derivatives, and we square the whole thing, and that gives us the Lagrangian. And we could work it out. Instead of having just one field, we would have four fields, but the same set of principles. But there is a bit of a shortcut, not so much a shortcut, but a simplification that can be made that's very helpful. And it really does illustrate some things about this idea of gauge invariance, which are quite important. Remember that the vector potential is not unique, that there are changes you can make in the vector potential that don't change the physics. You can use that freedom to simplify things. You can use the freedom that you have, which is almost like a freedom in your choice of a coordinate system. All kinds of freedoms are in physics associated with conventions, associated with coordinate frames, associated with gauges. You can use your freedom to simplify a problem by saying, I'm not going to work with the full general vector potential, but I'm going to use my freedom to do something a little bit simpler with it. In particular, let me first remind you what a gauge transformation is. A gauge transformation is you add to A the gradient of a scalar. Any scalar function. I can use this freedom to pick S in a way that may simplify my choice of A. For example, here is a particularly simple simplification that you can make. I'm going to choose S in such a way that the time component of the vector potential is 0. Can I do that? Is that possible? Is it possible to choose an S so that given any time component, given any A naught, given an A naught, is it possible to pick an S? Now, mu is the time component, so this means d by dt. If we start with the original vector potential with a time component, we change the time component by adding the s by dt. is it possible to choose S so that this is always equal to 0? The answer is yes. You can, given any function at a point in space, remember this is a derivative with respect to time at a fixed position in space. So you go to that fixed position in space, right over here, and you say, can I pick S so that its time derivative is minus some pre-existing or pre-specified A0? Can I choose S so that this is equal to minus the A0 by dt? Sorry, just minus A0. Well, yes, you can always find an S such that its derivative is any particular function. That you can convince yourself of. You do it by the S is some integral of A0. But given any function on the right-hand side, you can always find a function S on the left-hand side whose time derivative is equal to A0. Yeah.
All you have to do is go back to the original Leibniz convention. The minus sign.
There's not a question of the minus sign. It's a question of, yeah, that's right. But can you find, and the answer is yes, you always can do that. So if I choose the S so that its time derivative is minus the original vector potential component, time component, then the new vector potential, let's call it a prime mu, will have 0 for its time component. You can always do that. It's called fixing the gauge. It's called, or it's called fixing the gauge freedom. You have gauge freedom, meaning to say that you can change the vector potential without changing any of the physics. And so you make a choice. You make a choice, I will choose to work so that the time component of the vector potential is 0. There are other choices. There are other choices you can do. But in fact, that changes none of the physics. So we fix A0 equal to 0. That completely eliminates the time component of the vector potential, and all we have left are the space components of the vector potential, A sub m of x. All right, let's suppose we've done that. What then are the electric and magnetic fields? Well, the electric field, now the question is, shall I use my convention or Maxwell's? I will use Maxwell's tonight, which is minus my convention. In which case, there, let's see if I can remember it now. I can't. Yeah. Okay, it's minus, this is a vector, minus the A by dt plus gradient of A0. All right, but now I've simplified A0 and set A0 equal to 0. A0 doesn't exist anymore. And so the electric field, Maxwell's electric field, is just minus the time derivative of the space component of it. We can put some space indices. Let's put space indices, m. The electric field is nothing but the time derivative of the vector potential. What about the magnetic field? Well, the magnetic field only depended on the space components of the vector potential in the first place. It was just equal to the curl of the magnetic, curl of A. That doesn't change. The magnetic field has not changed, or the space components of that stays the same. B is del cross A, and electric field is now minus the A by dt. And that simplifies our lives a little bit. We don't have to worry about the time component of the vector potential. And the fields, the degrees of freedom are just the space components of the vector potential. We'll find out that simplifies life a lot. Okay, what about the Lagrangian? The Lagrangian, remember what the Lagrangian is in terms of the electric and magnetic fields? Yeah, it's F mu nu minus a quarter, but that happens to be equal to E squared over 2 minus B squared over 2. the square of the electric field minus the square of the magnetic field. Let's see if we can see it. There's the mixed space-time components. They get squared. Each component gets squared. So the mixed space-time components, those are the electric field squares. And the space components, those give you the magnetic field squared. Okay, so that's the Lagrangian. And now we can write the Lagrangian right in terms of these quantities here, in terms of the vector potential. The vector potential are the real fields that we use in the Lagrangian. And so let's write it down. It's E squared minus B squared, 1/2 E squared minus 1/2 B squared. 1/2 the electric field squared, but the electric field squared is just dA by dt squared. That looks an awful lot like this. 1/2 the time derivative of the field squared. Now, there's not just one term here, there are 3 terms here. There's ax squared, there's this time derivative of ax squared, there's time derivative of ay squared, and there's time derivative of az squared. But it is a sum of terms of exactly this type. 1 for each component of the vector potential. So the first thing we see is that there's a kinetic energy. There's a kinetic energy which is just the sums of squares of time derivatives of the basic fields. What about the second term? The second term is minus 1/2 b squared. B squared is minus 1/2 del cross A squared. Well, that doesn't look so different from this term. This term involves space derivatives. No time derivatives in here at all. Only space derivatives. Here there are only space derivatives. A curl only involves space derivatives. And A only has space components. So what we have here looks quite similar to what we wrote up here. Squares of time derivatives minus squares of various kinds of space derivatives. The Lagrangian looks nice and healthy. Doesn't have anything peculiar about it. And now we can apply exactly the rules that we derived before we took the break. In particular, let's think about the energy, the Hamiltonian. I don't have to go, before we do that, let me just tell you, we're not going to go through the whole operation. We can short circuit it. But you might ask, what is the canonical momentum conjugate to a particular component of the vector potential? In other words, by definition, the derivative of the Lagrangian with respect to the time derivative dt of A. Well, it's clearly just dA by dt. Let me be a little clearer about this. All right. There are 3 components, AX, AY, and AZ. These 3 components can be thought of as 3 fields. Each one is a degree of freedom of its own. Each one of them has a canonical momentum. That means the canonical momentum also has an index, x, y, and z. So let's call it pi x. This would be derivative of ax with respect to t. Pi y would be derivative of ay with respect to t. And likewise for pi z equals daz by dt. This, of course, here stands for time derivative of ax squared plus time derivative of ay squared, etc. All right, so the pi quantity, the canonical momentum, also has an index, and the index is simply associated with the index of A. But it's also true that the time derivative of A is just minus the electric field. So we found something interesting. The canonical momenta happen to be just minus the components of the electric field. For what it's worth, the physical meaning, in this case, the physical meaning of the canonical momentum conjugate to the vector potential is just the electric field. That's a sort of by the way, just notice the fact. But now let's take this Lagrangian and ask what the Hamiltonian is. We could go through the construction of the Hamiltonian, but we don't really have to. And the reason is we can look at this Lagrangian and say, look, here's a kinetic energy term that depends on squares of time derivatives, and here's a potential energy term that has no time derivatives at all. So this is kinetic energy minus potential energy, and we know what the answer is. The answer is going to be the kinetic energy plus the potential energy. That's it. So we can guess. The Hamiltonian and the energy is going to be 1/2 E squared, that's this term, A dot squared, plus 1/2 B squared. That's the correct expression for the electromagnetic field energy in an electric and magnetic field. We're setting the speed of light equal to 1. Setting the speed of light equal to 1, 1/2 E squared plus B squared. It's analogous, everything is entirely analogous, although not identical, to the Lagrangian here being phi dot squared over 2 minus gradient of phi squared, and the Hamiltonian being phi dot squared plus gradient of phi squared. Notice that again, same pattern. The Lagrangian is not positive, necessarily. In particular, if there's a magnetic field but no electric field, the Lagrangian is negative. But the energy is positive, E squared plus B squared. So what does this tell you? For an electromagnetic wave moving down an axis, remember what the electromagnetic wave looked like. It had an E component in one direction, and then in the perpendicular direction, it had a B field. The B field in magnitude was the same as the E field, in phase with it, but polarized in the perpendicular direction. And this tells us that the electric and magnetic field energies are the same. There's field energy in the electric field, there's field energy in the magnetic field. That electromagnetic wave moving down the axis has both electric and magnetic energy, and they happen to be the same. 1/2 E squared plus B squared is just twice either one of these. Okay, so that's the field energy. Any questions about the field energy? The next question is the momentum density. We go next to the momentum density. How much momentum is there in an electromagnetic wave? Okay, so let's go back to inertia. Let's do it up here for this field over here. We said that the field momentum was equal. The momentum density, let's call it the field momentum, is equal to the integral dx of pi times d phi by dx. I remind you where that came from. Pi is the canonical momentum, and d phi by dx is the amount the phi changes when you move a little bit. So this is the conserved quantity, conserved by virtue of Noether's theorem. It contains a pi, and it contains a d phi by dx. If there were several fields in the problem, we would add them up. And there are several fields in this problem. But that's all it is. This is a collection of 3 fields. Each one does exactly the same thing here. Instead of pi, we'll have the electric field. Pi is minus, I guess, the electric field. And instead of d phi by dx, we'll have dA by dx. That's all. So it's basically the same structure, and we can say that this is going to be replaced by the integral over dx of pi, which is related to the electric field, I will bet you that, I don't have to bet you, I am certain that I don't know the sign that goes here. Offhand, I would have to figure it out. It would take me some time to figure it out. But let's just not worry about the sign. The mth component of the electric field is a particular canonical momentum, and then that gets multiplied by dA sub m by, okay, let's get it right. E sub m dA sub m by dxn, and this is summed on m. All right, so let's get the idea here. If there are several fields in a problem, let's take the nth component of momentum. The nth component of momentum along the along the nth axis. That's this. Momentum along the axis n is pi d phi by dxn. If there are several fields in the problem, we add them all up. Well, there are several fields in the problem, and the several fields in the problem are the three components of the vector potential. So let's add them up. Derivative is with respect to xn, and that defines the nth component of momentum, but we have to sum over m. All right, so n is summed over. I won't bother writing a summation sign. We'll use the summation convention. This is the momentum in the field. Electric field, this is the p sub n, the nth component of momentum. Okay, so total momentum, p sub n, is an integral over space.
What you do have minus, the momentum is minus E sub m.
Yeah, I've lost the sign. I can't keep track of the sign. Yeah, I'm not sure. P sub n, apart from a sign, is E sub m dA sub m by dxn. M being a summation index here. Now, this is a little bit funny. This dA sub m by dxn, it's very tempting to want to put minus dA sub n by dx sub m. Why do I say that's tempting? Because you really want to put the magnetic field there, not just some damn thing with the vector potential in it. Okay, so let's ask, what damage does it do to P if I did put this extra term there? Does it change it? Right, so let's focus on this thing that I added in, integral E sub m dA sub n by dx sub, no, dAn, yes, by dxm. I added that thing in, or I subtracted it off. Well, I suggested that maybe it's okay to do that. All right, maybe. All right. And this is integral d cubed x. All right, now, by now, I hope everybody knows how to do an integral by parts, a partial integration. Whenever you have an integral like this with a derivative on one thing times another, it's equal, assuming you're making an assumption, namely that the fields go to 0 far away so that there are no boundary terms. But you can take this derivative and shift it to the other factor at the cost of a minus sign. This is equal to minus the integral dEm by dxm an. You can just take the derivative from one factor put it on the other factor, and put a minus sign. That's called integrating by parts, and we've done it over and over and over. This is just another example of it. But what do we have here? The divergence of the electric field, del dot E. And that's one of Maxwell's equations, that del dot E is equal to 0. So this integral, this added term in the integral, doesn't contribute anything. That means that the total momentum can be written in terms of the electric and the magnetic fields. This is EM, this is actually E cross B. If you work it out, you'll find out that, that the momentum is equal to E cross B. Again, the sign I've forgotten, I don't remember. E cross B is the momentum density, dx, d cubed x. E cross B, cross product between E and B, is the momentum density. It's a vector. It is a vector, so the direction of this vector tells you the direction of the momentum. If you have an electric and magnetic, for example, if I create an electric field by taking a capacitor, plus, 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 minus, 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 the electric field goes that way. And let's see, I want to make a magnetic field going into the blackboard, so I put North Pole and a South Pole. And in here, there's an electric field going one way, magnetic field going the other way, and the cross product, which goes in which direction? Or that way, I'm not sure. That way, okay? That means locally in here, there's a momentum density. There's a momentum density of a momentum that's moving to the right. That's the meaning of it. This is called a pointing vector, incidentally. Pointing, not because it points in the direction of the momentum. Pointing, P-O-Y-N-T-I-N-G. Pointing was as a name, yeah.
Del dot E is 0 because there's no...
If there's no charge density, that's right, assuming there's no charge density, yeah. In other words, for a free electromagnetic wave. If there is charge density, you have to account for the momentum of the particles making up. So at the moment, we're just doing pure electromagnetic fields with no charge density. That's right. That's a good point. All right, so let's just, as the last thing, just let's look at this expression for an electromagnetic wave. We have an electromagnetic wave with an electric field, for example, pointing up over here. Let's say a magnetic field pointing out of the blackboard over here. You move down a ways. The electric field is down, a half wave down, and the magnetic field is into the blackboard. Which way is E cross B? Well, let's start over here. And then, of course, it keeps oscillating. Electric field up, magnetic field out, electric field down, magnetic field in, go a little further, electric field up, magnetic field down. Which way is E cross B? Is it to the right or the left? Okay, so the momentum is going this way over here. What about over here? Same direction. Both E and B have changed sign, but E cross B stays the same. And so there's momentum flowing here. And of course, that's the direction of the wave. The wave moving down the z-axis carries a momentum which is E cross B. Notice how important it is that E and B are perpendicular to each other. If they weren't perpendicular, that's not a solution to Maxwell's equations, but if they weren't perpendicular, it wouldn't carry any momentum. So the momentum, the pointing vector, is a consequence of the perpendicular nature of E and B, but it all traces back to Emmy Noether's wonderful theorem about the connection between conserved momentum and translation invariance, spatial translation invariance. So it's all coming home in one big piece: classical mechanics, field theory, electromagnetism. It's all the same stuff. It's all the same stuff. It's all principle of least action. And I think that's probably a good place to stop. Yeah.
I know you did this several times, but I'm having trouble keeping track of the points of contact between the vector potential and the things that we're calling the E field and the B field.
Yeah.
So what are the places where those things hook up?
Well, here's a rule. Oops. Electric field is equal to minus. Let's take the nth component of the electric field. Minus the derivative of the nth component of the vector potential with respect to time plus the derivative of the time component of the vector potential with respect to xn.
That's Maxwell.
So again,
Maxwell's E or yours?
I think this is Maxwell's. Yeah. Yeah, for some reason, I've always been prejudiced to call the electric field plus the ADT. I like the idea that the electric field is the canonical momentum conjugate to A. And, you know, I've believed that for at least 40 years. So probably intermittently, I knew that it wasn't, but right. Notice, incidentally, that the expressions for the energy density and so forth, those don't change when you change, but the E cross B does. So you got to be careful. You do have to be careful. Okay, this is the expression for the electric field. The magnetic field is just B equals del cross A. Now, if you do this trick of fixing the gauge, of using the gauge freedom to set A naught equal to 0, then it's easier. The electric field is just the time derivative of the gauge potential. So it's electric field time derivative, magnetic field related to space derivatives. Yeah.
This might be also what he was wondering, but is the A field in some sense more fundamental, or is it just like the
Well,
part of this?
I think it's more fundamental. No, I think it's more than a. I think there's some questions you have to answer for yourself. If you can't formulate the theory with just the electric magnetic fields, and you need the vector potential to formulate the theory from the beginning, I think you would say that they're more fundamental. On the other hand, there is this obscure fact that the vector potential is itself not unique. Therefore, it's not a measurable thing. All measurements are unchanged by a gauge transformation. So, on the one hand, it's more fundamental from the point of view of the mathematical formulation of the theory. From another point of view, it's not directly measurable. So you have to accept it for what it is.
So it can't exert a force.
That static field you have on the capacitor that you put up there, is it true that the momentum is 0 of that field?
Which field is that now?
Where you have if you lift the board up there, where you have the capacitor and you have the magnetic field going.
The total momentum must be 0, I think. Yeah.
It has energy, right?
Yes, it has energy. Yeah.
Question about, I remember some 60 years ago learning that the Poynting vector was the power density.
Yes.
And
Good. Okay. Good. So let me. Good. Yes. All right. So that's correct. The Poynting vector has two meanings, and I'm going to tell you about them now. All right. That goes back to the energy momentum tensor. Remember, first of all, T naught mu is the density of the muth component of momentum. Now, let's make it's got two indices, it's quite clear, it must have something to do with a tensor. All right. As we move along the horizontal axis, we're changing this thing here. This is energy, let's call it P naught, and Px, Py, and Pz. These are the things, the quantities whose density we're talking about. Let's see, do I have that right? This is varying from here. I think so. And what about vertically? What about vertically? Well, for vertically, we go back and we remember, suppress this index here, and just think of this as a density of something. As a density of something, it's similar to J naught. Well, J naught also has Jm associated with it, which is the flux of that quantity. So it sounds like maybe there's a bigger quantity that includes T nu mu. When nu is spatial, it means a flux. When nu is time-like, it means a density. All right, so this here would be, the density here would be T naught naught, T naught 1, T naught 2, T naught 3. These would be the density of energy, the density of Px, the density of Py, and the density of Pz. Then we would come down a row. We would have T1 naught. This would be, read it down vertically now, and think of it vertically as T1 naught, T2 naught, T3 naught. And what the meaning of this is the density of energy, the flux of energy in the x direction, the flux of energy in the y direction, and the flux of energy in the z direction. All right, so the second index here says energy. The first index says density, flux, flux, flux. Then we come over here. T11, T21, T31. This is the density of x component of momentum. This is the flux of the x flux of the x momentum, the y flux of the x momentum, and the z flux of the x momentum. What does it mean, the z flux and the y flux? It means the amount of x momentum that's passing through a window oriented in the y direction. Okay, so it's a little tricky, and so forth. This whole thing forms a tensor. It's not obvious that it forms a tensor, but it does form a tensor. And what is more, it forms a symmetric tensor. Now, this is not something I'm going to prove tonight. It forms a symmetric tensor, which means that T naught 1 is the same as T1 naught. Let's think about what that says. This is the density of x momentum, and this is the x flux of energy. X flux of energy equals the density of x momentum. All right, we worked out the density of momentum, and it was the Poynting vector. What I didn't tell you is that it's also the flux of energy. The flux of energy is what you call the power, what did you call it? You gave it a name, the power density? The power density? Yeah, the power density. It's the flow of energy. So the flow of energy along an axis is the same as the density of the momentum along that same axis. Density of momentum equals flux of energy. The Poynting vector, therefore, has two meanings. All right, the Poynting vector, here's the Poynting vector, pointing, P-O-Y. It's formed from a cross product of an electric field, pointing. It has two meanings, okay? It's the flow of energy, and it's the density of momentum. If you're, and as a flow of energy, you can think of it as the power per unit area flowing through a region. Good. All right. So this energy momentum plays a really big role in general relativity, and we will come back to it. We'll come back to it and think of it in a totally different way. But I'm glad we got to it this quarter. I was a little afraid we wouldn't get to it, and I wanted to get to it so that we would have it as a basis to start general relativity next time. In general relativity, the energy momentum tensor is the right-hand side of Einstein's field equations, so it's not an insignificant quantity. Okay, good. Thank you.
For more, please visit us at stanford.edu.